Okay, so if you've ever looked up at the night sky, I mean, really looked and wondered about those huge ancient star clusters, the really bright, dense ones.
Globular clusters, yeah. They're pretty spectacular.
Exactly. Well, it turns out astronomers have been scratching their heads about how they even formed for something like 400 years.
It's genuinely one of astronomy's longest-running mysteries. How did these massive, dense balls of stars come together and stick around for so long?
Right. And today, we're doing a deep dive into some fascinating new research. This is from the University of Surrey. It seems they might have cracked it.
And not only that, they might have stumbled onto a whole new type of cosmic object that was sort of hiding in plain sight.
Okay, so that's our mission for this deep dive. We're going to unpack these huge simulations. They call them EDGE.
Yep, the EDGE simulations. And we'll explore what these potential new objects, these globular cluster-like dwarfs, could mean for, well, some pretty big questions.
Like dark matter and maybe even finding the universe's very first stars.
Exactly those. Big stuff.
All right, let's start with the basics then. The puzzle itself.
Oh.
When we say globular cluster, what are we actually talking about and what's the core contradiction?
Okay, so picture a swarm of stars. Not just a few, but hundreds of thousands, sometimes millions.
Oh, wow.
And they're packed incredibly tightly together. They orbit larger galaxies, like our own Milky Way.
And they're old.
Incredibly old, among the oldest things we can see in the universe. And crucially, the stars inside them are remarkably similar, same age, same basic chemical makeup, very uniform.
Okay, ancient, dense, uniform. That sounds like a recipe for something stable. But you mentioned a contradiction, the thing that stumps scientists.
Right. Here's the kicker. You look at almost any large structure in the universe, galaxies, even small dwarf galaxies, and they're held together largely by gravity from unseen dark matter. There's loads of it.
That invisible scaffolding everyone talks about.
Precisely. But when astronomers measure how stars move inside globular clusters, they find basically no evidence of dark matter. None.
Wait, hang on. So these massive ancient things are packed with stars, but they don't have the extra gravitational glue from dark matter.
Exactly.
How do they not just fly apart then? Isn't that the fundamental problem for the models?
That is the fundamental problem. If you tried to simulate cosmic structure formation using standard models, you'd expect these things to either have dark matter or, well, potentially dissipate.
So previous attempts needed some kind of special starting conditions, like tweaking the simulation.
Often, yeah. Which isn't ideal if you want to see if they form naturally from the universe's own evolution. You want them to just emerge.
Okay, so the goal for this Surrey team was clear. Build a super realistic virtual universe and see if these clusters just pop up on their own without any special fiddling.
That was the plan, and it meant using some serious computational firepower.
These EDGE simulations we mentioned, how big are we talking?
We're talking ultra-high resolution simulations tracking 13.8 billion years of cosmic history. They ran these on the UK's Dirac National Supercomputer Facility.
Dirac.
And get this, they ran for years. If you tried to run the biggest simulation on, say, a really good gaming laptop,
Yeah.
it would take decades, maybe longer.
Decades.
Yeah.
Just to see if star clusters form correctly,
Bam!
that's commitment.
It shows how complex these processes are. But that computational muscle bought them incredible detail.
The resolution, right? What was it?
Down to just 10 light years, which sounds big, but cosmologically, it's fine enough to capture the impact of individual exploding stars' supernova.
So you can see how the energy from one star blowing up affects the gas and star formation nearby.
Exactly. That level of physics, the feedback, is crucial for getting realistic structures.
So the moment of truth.
Yeah.
They run this incredibly detailed decade simulation on a laptop universe. Did the globular clusters appear naturally?
They did. The simulation showed pretty conclusively that globular clusters do emerge naturally within this standard cosmological framework.
Okay, so no dark matter needed for them specifically.
Correct. Professor Justin Reed, who led the study, mentioned they saw them forming through at least a couple of different pathways in the simulation, neither of which required a pre-existing dark matter halo for the cluster itself.
So the basic physics of gas, gravity, and stars exploding is enough to make these dense little balls of stars. Mystery kind of solved.
The formation mystery, yes. It confirms the underlying physics works without needing weird extras for GCs, But.
There's always a but in science, isn't there?
Well, when you build a simulation this powerful and this realistic, sometimes it shows you things you weren't actually looking for.
Ah, the unexpected discovery.
Exactly. The Eddy GE simulations didn't just make globular clusters, they also produced this other class of object, something new.
Which they called.
The globular cluster-like dwarfs. Bit of a mouthful, maybe, but descriptive.
Okay. Globular cluster-like dwarfs. That name implies they're sort of in between. Like a cluster, but also like a dwarf galaxy.
That's precisely it. Visually, they might look very similar to a standard globular cluster. Dense, old stars, bright.
But structurally.
Structurally, they're different. They occupy this middle ground.
Okay, let's zero in on this because it seems really important for you listening. We said globular clusters have no dark matter, right?
Right, effectively none.
And dwarf galaxies are like swimming in it.
Totally dominated by it. Often 1,000 times more dark matter than regular matter like stars and gas.
So where do these new objects, these globular cluster-like dwarfs, fit on that spectrum?
They land right in the middle, but leaning towards the dwarf galaxy side in one crucial aspect.
Okay.
They look like a cluster, but the simulations show they actually do contain a significant amount of dark matter. They form inside their own dark matter halo.
Whoa, so wait. Through a telescope, it looks like a normal, old globular cluster.
Dense stars. Looks ancient.
But underneath, invisibly, it's actually got the dark matter scaffolding of a dwarf galaxy.
That's the prediction. It's like finding out some tiny, dense islands are actually the peaks of huge underwater mountains. The visible part is similar, but the underlying structure is completely different.
So astronomers might have already seen these things, cataloged them as regular globular clusters.
And totally missed the fact that they're fundamentally different structures. Dark matter havens hiding in plain sight.
That's fascinating. They've been camouflaged by their own stars.
Pretty much. The stars look the same, but the gravity holding them is different. That hidden dark matter halo changes everything about their nature and origin.
Okay, so finding these things for real, confirming they exist, what's the big so what? Why is distinguishing between a true globular cluster and one of these dwarf-like ones matter so much?
Oh, it's huge. It potentially gives us a brand new tool to tackle two massive astrophysical problems.
Okay, let's take them one by one. First, dark matter. How do these help?
Well, think about it. Dwarf galaxies are choked with dark matter, but they're also messy and complicated sometimes. Globular clusters have no dark matter, so they can't tell us much about it directly.
Right.
These new objects, if they exist, are the Goldilocks zone. They're relatively simple, like a cluster, but they have a dark matter halo. They sit right at the threshold.
So they're like a natural laboratory.
Exactly. Studying them could give us unprecedented constraints, as the researchers put it, on the nature of dark matter itself. We could test different theories about what dark matter is by seeing how it behaves in these specific environments.
Comparing the simulations to real observations of these specific objects.
Precisely. It's a much cleaner test bed than a giant, complex galaxy.
Okay, that makes sense. Dark matter testing. What's the second big prize? You mentioned first stars.
Yeah, the hunt for the universe's very first generation of stars. Population third stars, sometimes called.
Pristine stars, right?
Yeah.
Meaning they formed before the universe got polluted with heavier elements.
That's the idea. Stars made of basically just hydrogen and helium, fresh from the Big Bang. Before subsequent generations of stars cooked up things like carbon, oxygen, iron, and scattered them through supernova explosions.
Finding those would be like finding cosmic fossils, telling us about the universe right at the beginning.
Absolutely. And the theory suggests that the kind of smaller dark matter halos these globular cluster-like dwarfs might live in are exactly the sorts of places where these first stars might have formed.
So if we confirm these objects exist, they become prime hunting grounds for these elusive first stars.
Potentially, yes, because they're old, relatively undisturbed, and might preserve chemical signatures from that very early era, maybe even remnants of those first stars themselves.
This isn't just simulation land anymore, though. Do they have actual real-world candidates that might be these things? Objects we've already seen?
They do. The paper points to some possibilities among the known satellite galaxies or maybe misidentified clusters orbiting the Milky Way.
Any specific names?
They mention one called Reticulum 2. It's known as an ultra-faint dwarf galaxy.
Ultra-faint, so dim and hard to study.
Relatively, yes. But based on its properties, it looks like a strong candidate for being one of these transitional objects possessing characteristics of both a cluster and a dark matter halo.
So Reticulum-2 might be our first confirmed example if we can study it closely enough.
It's a prime target.
Okay, so you have the prediction from ADGE, you have candidates like Reticulum-2. What's the next concrete step? How do astronomers prove it?
Observations. Very detailed, very precise observations.
What kind? Just taking prettier pictures?
Not just pictures. We need spectroscopy. Lots of it.
Spectroscopy breaking down the light from the stars.
Exactly. We need to measure the light from as many individual stars within these candidate objects as possible.
And what does that tell you?
Two crucial things. First, by measuring the Doppler shifts in the starlight, you can map out how fast the stars are moving. That tells you the total gravity holding them together, which reveals whether there's unseen dark matter contributing.
Ah, measuring the gravity to weigh the dark matter.
Precisely. Second, spectroscopy tells you the chemical composition of the stars, what elements they contain. That confirms their age and helps check if they have the pristine signatures we talked about.
So you need powerful telescopes like...
James Webb Space Telescope is definitely on the list. Its infrared capabilities are great for peering into dense regions and studying faint objects, and also upcoming large spectroscopic surveys projects designed to get these detailed light signatures for millions or billions of stars.
So the hunt is on, basically, using our best instruments to check if the simulations got it right.
That's the next chapter, verifying the prediction.
Okay, so this deep dive has taken us from a 400-year-old puzzle about simple-looking star clusters
Through years of supercomputer number crunching.
to not only solving that puzzle, confirming they can form without dark matter, but also predicting a whole new kind of cosmic object.
These globular cluster-like dwarfs, defined not just by how they look, but by that hidden dark matter halo.
It really changes how we might need to classify things in the local universe.
It does. You can't just judge a cosmic book by its cover, apparently. What looks like a simple cluster might be structurally something far more tied to the dark matter web.
Which leads to a final thought to leave you with, maybe. If we've potentially been misidentifying objects like Reticulum-2 for years, classifying them based on appearance, while missing a fundamental structural component like dark matter, how many other structures out there in the vastness of space might we have similarly mislabeled, where an invisible factor completely changes what we think we're looking at?
That's a great question. It speaks to the challenge of observation and interpretation. We see the light, but the underlying reality, especially with things like dark matter involved, can be much more complex. The universe might be full of these kinds of subtle disguises.
Definitely food for thought. Thanks for joining us on this deep dive into cosmic simulations and hidden structures.